Good afternoon, and thank you all very much for coming along to what seems to be a very exciting afternoon of particle physics. If you read the blurb, we're going to try and cover 100 years of particle physics in just 1 hour, which is a ratio of about 876,582 to 1. So it's all of the physics in 0.000114% of the time. So my name is Matt Parker. I am a mathematician by training, so I am dangerously underqualified to be on the stage today. I'm just happy when the equations work out, to be entirely honest. Although these physics guys insist on then turning that into a falsifiable theory that they can test with an experiment. We're sponsored by Swansea University, which I'm going to thank solely in English. The Cheltenham Science Festival only gets 40% of its revenue from ticket sales. The rest is from sponsors and patrons and the like, so we are hugely grateful to everyone who's able to sponsor an event that makes the entire thing possible. So my only remaining duty between now and the Q&A, which will occur at the end, is to introduce our speakers. They will cover this in much greater depth. So just very quickly on, they're both sitting behind me, trying to pretend they're not here yet, if you've not spotted them. So on your left is Dr. Tom Whyntie, who is a physics researcher based partly at Queen Mary University of London, a fantastic institution who may have also given me a job. And on your right is Professor Mike Charlton. Got it, yes. Who is Professor of Physics at the aforementioned Swansea University. So can you please, to get everything off and racing, give them a huge welcoming round of applause.
Yes, good afternoon, ladies and gentlemen. I'm Tom Whyntie, and what we promise to do here today is to get through the entirety of particle physics in 40 minutes. Like he says, about 100 years' worth of physics there. So, yes, if you haven't switched your phone off, you can follow along with at Swansea Uni or at Whyntie on Twitter there. I don't know if anyone tweets like that. And yeah, see if your favourite bits of particle physics or what have you. Now, I worked on the compact muon solenoid experiment, one of the giant digital cameras at the Large Hadron Collider in CERN, Geneva. You may have heard about that. I don't know. But here it is. And if you look at it, it's the size of a cathedral. People say it's like a giant digital camera. It's more of a sort of an eye. I kind of look at it, sort of looking deep into your soul, probing every part of you. And in many ways, that's what particle physics is about. It's about looking at what we're all made of at the fundamental level. And that's what I hope to give you an insight, as well as Professor Charlton, an insight into today. So what are we going to look at exactly? Just to give you a whistle-stop tour of the whistle-stop tour, we're firstly going to look at what is particle physics. We're going to go inside the atom. We're going to look at antimatter, which is your speciality field. We're going to look at cosmic rays and particle accelerators, two different ways of doing particle physics that have been carried out over the past 100 years. We're going to look at taming the particle zoo, which will explain more in detail when we get to that point. But then finally, the crowning achievement of 20th century science, the standard model of particle physics, our best current understanding of how matter and forces work at the fundamental level. And that's kind of the coup de grace of the talk, if you will. And we'll end with the big questions in particle physics, i.e. the big unanswered things that we haven't quite, got around to yet, and that's what the LHC and indeed many other experiments, such as ALPHA, will be hoping to answer over the next few decades. So, what is particle physics? Well, as I say, it's like looking at the very fundamental, the Lego bricks that we're all made of. And part of that quest, part of that journey is actually hunting down these particles that we're all made of. So just to illustrate that, I've made up this picture of, it's a bit old now, as you can probably tell, but this is what we were doing, back in 2007, 2008. We were looking for this thing, the Higgs boson. This is one example. But it's one of these particles that we were hunting. And that's what the past 100 years has been about. It's been hunting for evidence of what we're all sort of made of. So that's where we start, really. But so you can say that you can either begin at the atom. This was the atomic theory was first proposed by Democritus in around 460 BC, and there he is. He's not a particularly handsome chap. He's got the beard thing going on. That's fine. But he was the first to propose that perhaps everything is made up of indivisible units called atoms. these sort of things that we can't split any further. And this is what sort of prevailed for, well, several hundreds, thousands of years even. But everyone was quite happy to just take it as read, take it as a given that, yeah, this is probably an okay thing to do. It wasn't until John Dalton in the late 19th century started actually putting some science, some experiments behind these ideas. And so he proposed that there were different ways of mixing chemicals together that showed that the fundamental unit was the hydrogen atom. This unit of element of hydrogen was the smallest possible thing, the atom. But even that wasn't taken seriously till a few decades later. I'd say our journey into particle physics, though, begins with the electron. This was discovered by J.J. Thomson in 1887 using cathode ray tubes, these sort of Crookes tubes, evacuated bits of glass where you could pass these strange glowing beams that he showed were actually particles. And what's more, they were particles that were thousands of times smaller than this hydrogen atom, which was previously believed to be the smallest thing. After that, you had Ernest Rutherford, who in 1911 showed that actually these atoms, the stuff that we thought everything was made of, weren't just kind of evenly distributed lumps of stuff. Everything in the atom was, well, most of the mass of the atom was concentrated at the very center in something called the nucleus. And he showed that by scattering alpha particles off gold foil and showing that sometimes they'd pass straight through, but sometimes they would bounce back as if hitting something strange and condensed in the middle. And he came up with the idea of the nucleus. And that kind of stuck too. So this picture of how the atom was actually something that was divisible, that wasn't just a solely formed component, started to take hold. And that's where I think particle physics really begins. So if we look inside the atom, we have the electron, 1887, J.J. Thomson. Further than the nucleus, we have the proton, which was Ernest Rutherford in 1918, and then later in 1932, James Chadwick discovered this uncharged version of the proton. The proton has a positive charge, of the neutron. So it's like a neutral equivalent. And they showed that these two things are actually was what is inside the nucleus. This is what's inside this condensed part inside the atom. Combined to that, you've got the photon. Now, there was this whole other thing going on with light. I don't have time to go into the whole story. But in 1905, Einstein suggested that light itself, was composed of chunks of energy called the photon. So we've got the photon there as well. And all of these things have, their own measured masses. So the proton and the neutron are about 1,800 times more massive than the electron. The photon, of course, is massless, and by definition, that's what makes it able to travel at the speed of light. So we've got these little components, and there's one little thing, extra thing to talk about, which is that the neutron, one of these larger parts of the nucleus, can in fact decay into a proton, an electron, and something else called a neutrino. And this was sort of ghostly sort of shadow particle that obviously no one could really detect, that also forms up the part of this radioactive decay. Now, so we've got protons, neutrons, electrons, and photons. Now, you can mix protons and neutrons together, as we say, to form a nucleus. You can add electron into the mix and actually get something like this, which is a helium atom. Once you get atoms, of course, you can start to do chemistry. And if you're really bored, you can do material science. Well, not bored. No, I mean, this is Mark Meadow, the next thing. Material science is lovely and very exciting, but you can do that. But when it gets really interesting is you can start to do complex chemistry. You can start to form molecules. And once you do that, well, then you can start to form DNA. And once you have DNA, you can have single-cell organisms, slightly more complicated organisms, plants, dinosaurs, mammals, gorillas, humans, until you reach the very pinnacle of evolution and the universe, Professor Brian Cox himself. And so the question is, which, you have to ask particle physicists, why, if you can do all of this with just protons, neutrons, electrons, and photons, and maybe neutrinos as well, why do you need to go further? And that's because that's what was there. And this is where I hand over to Professor Charlton to talk to me about Paul Dirac. So
okay.
I'll hand over.
Thank you very much, everyone. So something big was about to happen in the 1920s. What Tom's just described to you, the theory of the atom, was developed around about then. And those theories, some of them really work very well. They're still the workhorse of physics, low-energy physics and chemistry. You may have heard of the equation called the Schrödinger equation. It still works well in its own in its own region. But what everybody who was working in the field at the time knew was that that equation couldn't be the whole truth, because that equation does not balance up space and time in a way that's consistent with Einstein's earlier theory of relativity. So the race was on to find a new theory which did that. And so enter this gentleman here, Paul Dirac. Now, if you think this equation is bad, Tom's got something much worse later on, I can assure you. But in 1928, he wrote down this equation. It looks like a typical horrible physics equation, a whole bunch of stuff all equal to zero. There's a lot of things in there, and this W here is what we now call energy E. But if you turn off, this has got electric and magnetic fields in it. If you say, let's solve it, this equation, if we can, for the very simplest possible situation, this is an electron in space with no electric and magnetic fields. In other words, a free electron. You get a very simple solution. It's down there, it's a quadratic. If you then say, well, let's make it stand still and turn the momentum to zero, so you turn the momentum to zero in this equation here, you get E equals mc squared. But actually you don't. You get E equals plus or minus mc squared. And what Dirac found was that you could not ignore these negative energy states. So what were they? This was a huge furore at the time. Nobody really believed him. But it took him a few years to work this out. But what he realized was that these negative energy electrons could be completely filling the whole of vacuum. And we have a concept a little bit like that nowadays. But if they're completely full and uniform, you wouldn't see them unless something happened, unless you pumped some energy in. And this is what quantum mechanics is all about. The theory of the atom, it's about the energy differences between the levels in the atoms. And this is a little bit like that, except it's a large amount of energy for an atom. But if you can pump in twice the rest mass energy into that system, you can create an electron and a positron. So you can create the absence of an electron. A negative energy electron is a positive energy, positively charged particle. And this was Dirac's brilliance. It took him a little while to get to it, but in 1931, he wrote a remarkable paper. This is a paper on a completely different topic, something you never do nowadays. At the beginning of this paper, he sorted out what the problem was with the negative energy states. Nowadays, it would be several papers. You wouldn't get away with putting that. You would never do that nowadays. And this is what he wrote in 1931, the positron. We should not expect to find any of them in nature, rapid, as we call that, annihilation, but if they could be produced experimentally in vacuum, they'd be quite stable and amenable to observation. The last 18 words of that are affected with my entire scientific career. And 2 paragraphs further on, he predicted that the protons would have their own antiparticles. Absolutely remarkable prediction. So in those days, there were no particle accelerators. The only way you could get high-energy particles was to look at cosmic rays, which were discovered in 1912 by Victor Hess, who took machinery up in a balloon. But by the 1930s, they'd invented cloud chambers, and here is Carl Anderson sitting in his lab. There's a cloud chamber photograph of a positron. There's an electromagnet, so there's a magnetic field across there. So the charged particle curves in there. And the most important thing on this is this thin lead plate. I think you can see the curvature is greater there than here. And that the way that tells you that it's a positive particle going that way, because you can tell the direction of motion, because it has to be going downwards, because it's passed through the lead plate and lost some energy. So that was the first picture of an antiparticle. Okay? Around about the same time, the discovery was made by Blackett and Occhialini. This is a more complicated thing. There's a lot of showers here, and this is production of an electron and positrons in pairs by high-energy gamma rays. And when we produce them, we always produce them in pairs, okay? They always come together. If you make a positron, you have to make an electron. That's the laws of physics. And that's an early observation of it. And I think Tom will say more about that later on, because we think they always have to come in pairs. But something has happened to the antimatter. The antiproton, how much energy is needed for that? Well, you need rather a lot of energy for antiprotons, so you need to go to an accelerator. Okay, so it's 938 MeV in those units, and that's the reaction you would use to produce it. So the age of accelerators had to begin. He's one of the very first ones. This is a cyclotron. Here, there's a constant magnetic field. The particles are injected in the middle, and they're accelerated as they pass through this middle bit, and they just come out in a spiral out one of these arms. That's a rather limited machine. So later on, they invented a synchrotron-type machine where there was only one radius, and the particles went round one radius. You accelerated them in there. These are all magnets confining them. You've accelerated them in this machine, but when you accelerated them, you had to change the magnetic field in tune to keep them in line. So the machine that by 1955, this machine had been made in California in the States. It's called the Bevatron, or was called the Bevatron. It stands for the billion electron volt atron. So that's 10 to the 9 electron volts. And it's this one that was used in the discovery of the antiproton. So there's the Bevatron beam. It hits a target. Some things are coming off. It's starting to look a bit like a modern particle physics experiment. There's magnets here deflecting things and detectors out here of one sort or another. So there's the electron volt beam and the beam line. And there's so you use all of these things to separate particles out according to their mass and their charge, and you can time them as well. And there are the first antiprotons. And I think it's time for me to hand back to Tom. So the age of the accelerator was upon us.
Yes, and not only did it bring the discovery of things like the antiproton and the antineutron, i.e. the antimatter equivalents of the particles that make us all up here. It started to bring in a lot more new particles. And in fact, the cosmic ray experiments of the time also threw up a lot of particles that people hadn't been expecting. And this is where particle physics started to get interesting and a little bit sort of dangerous. And I'll explain why that is. It's because of the particle zoo. Physicists hate things that are complicated and when you have to name things. That's why we don't go into biology, right? That's why we stick to keep things very simple. But at this point in the 50s, we had not just the proton, the neutron, the electron, and the positron, its antimatter equivalent, but we had things like the muons, which are like fatter, heavier electrons that punch through things and showed up in cosmic ray experiments too. We had things like the pions, the kaons, the sigma, all of these things. And physicists were now having to start to classify and write all these down. And in fact, one Nobel Prize-winning physicist, I think it was Lamb, who said, rather than getting a Nobel Prize for discovering a particle like Thomson did, like Rutherford did, and what have you, rather than getting a Nobel Prize, physicists should start to get a $10,000 fine every time they discovered one like that. Because it was just getting rid of... I mean, look at it. This isn't nice. This isn't pretty and elegant and symmetric. And it got worse. More neutral pions, neutral kaons, neutral sigmas, deltas even. I mean, they just started running out of Greek letters, basically, at the end of the day. And so this was the fundamental problem with physics at the time. It wasn't until the theorists started coming along and going, well, okay, let's... the mathematicians even, Matt, who started to help out here. It was very big of them. So what they noticed is if you took some of these particles, the pions and the kaons, and arranged them by some of their properties. So there was one property at the time called strangeness, because some particles seemed to be a bit strange. It was all a bit strange. They're not good at naming things. This is a theme that runs through the talk. I don't know if it's the Bevatron, I don't know. Anyway, it's not it's a Beverly. I don't know. Anyway, someone didn't like their ex-girlfriend. I don't know. Strange. If you arrange them by strangeness and their charge across the bottom, they started to notice patterns. Now, physicists like patterns. This is a good thing. So we could arrange them. And it was Murray Gell-Mann who first started to arrange them like this. And once you start to arrange things in patterns, just like with the periodic table, you can start to make predictions. And they did. And they predicted that there should have been, according to the mathematics behind this, there should have been two new particles that they could then look for in their accelerators here. And that's what they did. And they discovered the eta and the eta prime. Yeah, I know. Just adding a little dash to it doesn't make it any better, I know. But never mind. But they managed to use, and this is what science is about. You have your theory, you notice patterns, and you make predictions. And that's what it did beautifully. So some time of order was coming to the particle zoo, and this was great. And actually, they took it even further than that. They noticed that actually, if you did this, you led to the prediction of something called quarks. So actually, Murray Gell-Mann, who turned the name quarks, or quarks if you're American, or wrong, as I like to call it, They said, quarks. So actually, we'll propose that everything is made up of three separate more simpler, more fundamental particles. And at these particles, and then you have the antimatter equivalents as well, and they have charges plus 2/3, minus 1/3, and what have you. And if you add them up like that, suddenly this crazy particles starts to make sense. So if you have your quark cross your antiquark, as you do in the group theory, you can see that these particles are actually made up of pairs of quarks. And this is great. So rather than this 8 big bustling zoo of particles, you've just got 3 quarks and their antimatter equivalents. Much simpler, much more elegant, much more physics, and that's good. So this new picture started emerging around the 50s to 60s, where you had not just your electrons, your muons, and their antimatter equivalents, but you now have the quarks. So these things are on your right here are the leptons, and the things on the left here are the quarks. And these are the matter particles, the particles with the stuff that we're all made of. Now, as you can probably guess from this diagram, the story doesn't finish here. And this is where I gloss over decades of hard work by physicists and scientists by simply saying they then discovered that they had, well, charges and things, but they started to build something called the Standard Model. So they then discovered the charm quark in the 70s, and that took a lot of accelerators and work, but it's just a few circles on here. And likewise, there was then the bottom quark, which was then much heavier. So these things get heavier as you go across. So these are the lightest ones, the things that neutrons and protons are made of. The charm and strange are another pair like that. But then you've got the bottom and the top quark, or as some people like to say, the truth and the beauty, because it's more poetic and you don't have to then start naming things like bottomonium, which just gets embarrassing in physics talks and serious conference papers about bottomonium. It doesn't work. So truth and beauty, I don't know, it's a little more elegant. And these things, they then also discovered in the 70s, were held together by something called gluons and the strong force. So in addition to all of these matter particles, the leptons and the quarks, you've got the forces. Now, the electromagnetic force is conveyed by the photons that we've already met with Einstein, but the gluon is like the equivalent of the photon for the strong force, the force that binds all the constituents of the nucleus together. It's what holds all the stuff in the middle of the atom together like that. And this is done by the gluon. This was found in the 70s as well. And then on the lepton side, they found that, well, if you've got 3 generations of things in the quark side, why not in the leptons too? And so they did. So they had electrons, muons, and then taus, which are even bigger, heavier sort of particles than the muons as well. And they had their neutrino equivalents too. And these were also discovered throughout the 70s and 80s. And this is how the Standard Model was basically sort of pieced together over this sort of the last 50 years or so. Now, the most... we mentioned earlier that the neutrons decay into protons and electrons and neutrinos, but there was also a great time, which unfortunately we'll have to skip over slightly, but they realized that this was down to another fundamental force called the weak force. And the equivalent of the photons and the gluons for this was things called the W bosons, the plus and the minus, and something called the Z bosons. And these were discovered in the 1980s. So they're about the same year I was, about the same year. I'm about as old as the bosons. They're coming up to their 30th anniversary, which is a little depressing in some ways. But anyway, yes, so these things were the force carriers for the weak force. So you've got the 3 forces of nature, well, the 3 that we can describe like this: the strong force, the electromagnetic force, and the weak force. But further than that, they realized that actually this weak force here was the same force as the electromagnetic force at high enough energy. So they managed to unify these 2 things together into one glorious force. And this pretty much was the Standard Model of particle physics about a year or 2 ago. You can see where this is going. Now, there was one big puzzle. Oh, and here's that equation, by the way, that we promised. This is so if you thought that Dirac one was bad, you can actually write this down as a single mathematical equation. Now, you'll notice the obvious mistake in it. This is only the first page. There's a second page that you all knew was missing. But yeah, this describes basically everything, all the forces, all the matter that we are made of in one simple, elegant, beautiful equation. And like I say, that's what we like in the physics. Now, I was a bit cheeky there in saying that the Standard Model was complete at this point. It obviously wasn't. There was one final piece to the puzzle that kept physicists awake at night. So we've got these W and Z boson things, and what's odd about them is that they're force carriers. And they carry this weak nuclear force which is responsible for radioactive decay, but it doesn't have a very great range. It's weak. That's why it's called the weak force. And they realized that the reason for that was that because these particles have mass. They're actually massive and actually about 80 times greater in mass than a proton. Whereas the photon, which is supposedly unified in this sort of force picture into something called the electroweak force, they're supposed to be the same thing, but these particles have mass and the photon doesn't. And people didn't understand really what. They had a guess why, and you may well have heard that this is because of the guess was this thing called the Higgs boson, the God particle, if you will. People hate calling it that, but in fact, there was an interview in the Times yesterday where, Peter Higgs wasn't too happy. But anyway, yes, so this thing couples to the W's. It interacts with the W's, giving them mass, and also to things like the quarks as well, but has no interaction with the photons at all, which is what makes them massless. And there are a few, there's the guy himself. He was around here yesterday, if you managed to catch him. Lovely chap. But the Higgs mechanism, again, I've got a question mark there, because there are also these guys here, these 5 guys, Englert, Brout, not Humperdinck, Englert, Brout, Guralnik, Kibble on the end there as well, and who am I missed? Oh, that's going to be awkward. Guralnik, did I say Guralnik?
You said Guralnik.
Yeah.
Okay, it's the other one.
EBHGHK is what in my thesis I referred to it as the EBH. I played it safe and just said, EBHGHK. K, who's that? Anyway, we'll come back to that. You can ask them the questions later. But there's also 5 people. But it was definitely Higgs who proposed the boson. So calling it the Higgs boson is fine. Higgs mechanism, not so clear. So what is a Higgs boson? Well, there are lots of different ways of thinking about it. David Miller of UCL said it's like a celebrity walking across a crowded room, much like Higgs was yesterday, actually. He was sort of surrounded by people and he couldn't get his way through. And that's what sort of slows him down. It's like him having mass. And the Higgs bosons are the people in the crowd. John Ellis, King's College London and CERN, says it's like walking over a field covered in snow, and the Higgs bosons on the snowflakes. So if you're a skier, you can glide right across like a photon. If you're really heavy or just wearing the wrong shoes, you're sinking in this Higgs boson snowfield. Okay. Ian Sample in The Guardian said it's like ping pong, slightly less technical. No disrespect to The Guardian, but it's ping pong balls and sugar on a tray. It's what he did when they discovered the Higgs at the time. And the Higgs bosons are the sugar grains. To be honest, there's no really good analogy that explains what the Higgs boson really is. So we'll just say it's there. We discovered it. We're happy. So how do you find a Higgs? Well, it's basically down to this fella. The Higgs boson has a mass itself, we think. Well, we know now it does. What was that? All slides. And he has a mass, so you need to create a lot of energy. And you do that with a Large Hadron Collider. And this is an aerial view of the 27-kilometre underground concrete donut in Geneva. I've superimposed that circle on there. That's not really there. They wouldn't like that in Switzerland. They'd get quite cross. Yes, under the ground, so here's a cartoon picture. About 150 metres under the ground on average, you have this giant tunnel, which has these superconducting magnets. There you go, expanded view of that. And the 2 general-purpose detectors, CMS on the left, the red team, the good guys, and on the right, the Atlas detector. And these are the bad guys, the blue team. That's how it normally is, right, I think. And these general-purpose detectors, their mission was to find the Higgs boson. And here's a picture, just to give you an idea of the scale of these things again. These are people. I don't know if you can see them on there. And this is just the middle section with our 3.8 Tesla magnetic field. Science doesn't get any bigger than this, really. And that's what particle physics is all about. So, cut a long story short, we found it. 4th of July, 2012. There's Rolf Hoyer, Director General of CERN. It's not there, obviously, in his hands. That's just an unfortunate photo. He was obviously very excited. But it was genuinely moving to see, not that event display, that wasn't genuinely moving. That's just a candidate event of the Higgs decay into 2 photons. But here's Peter Higgs himself embracing Fabiola Gianotti, spokesperson for the Atlas experiment at the time, on the big day itself. And he was credited saying, "I'm rather surprised that it happened in my lifetime," bless him. So he saw this, he proposed this thing in the late 60s, and thousands of physicists and engineers have dedicated their lives to discovering this thing, and finally they did, and he got to see it. So fingers crossed for November, Nobel Prize time. And here's the paper with the observation in CMS, and here's just a little... I should point out that there are about 3,500 people. You have to do Control F to Control F, type your name in. It's not as glorious as it sounds, but it really does emphasise that it's a huge team collaborative effort, and that's what physics and science is really all about. That's why I love particle physics. So I'd say that that's physics pretty much solved now. With the Higgs boson done and what have you. But there are, believe it or not, several big questions in physics left. And I shall hand over back to Professor Charlton to take us through some of those.
So, I'm going to start with the first one of these questions. And the first one is, where did all the antimatter go? Antimatter, as I told you, was discovered in the 1930s. It's been around us. We've got used to it. We know that it has to exist. And it's deep and fundamental in physics. But for some reason, there's none of it out there in the universe, or seemingly so. So when we exist in this part of the universe here, this is a rather dull and boring universe in comparison to what it was here. The slide's not dull and boring, it's started to wiggle about. Okay, but anyway, we live out here where atoms and molecules can form, and the universe has cooled right down. We're able to exist because we live next to a local hotspot in the universe, the sun. If it wasn't for that, it's very cold out there, 3 degrees Kelvin most of the place, and nothing much happens. It wasn't like that at the start. The universe was created in a big bang, but when it cooled down, several things happened. You probably can't read that or that, but these two events happened at some point during the cool down, and that says disappearance of antiquarks, and that says disappearance of positrons. So the disappearance of the antiquarks meant that no antiprotons were made and no antineutrons were made, and the disappearance of the positrons. This is really spooky, to me at least, because these are two completely different types of particle, as Tom explained, yet for some reason all of the antiparticles, we think, disappeared. So when the universe became cold enough, at about 10,000 degrees Kelvin, for atoms to start to form, there was no antihydrogen. There were no antiparticles there to form antihydrogen. So there's quite a lot of research going on to try and find out what happened to all the antimatter. So one way of doing that is, it's a funny how the way things that go around come around. So studying cosmic rays was where particle physics started, but studying cosmic rays is still a big area of science. One of the reasons is that some of them have absolutely colossal energies, higher than anything we could ever produce on Earth. But the other reason to study them is to get up there, out into space, and actually see what is hitting the Earth and where it might be coming from. So there's actually a particle physics experiment right now sitting up there, bolted onto the outside of the International Space Station, and it's called the Alpha Magnetic Spectrometer. We're a bit over alpha here because my experiment is called Alpha 2, but I'm not involved. Oh, it's got an extra E in it there. But it's sitting there, and what this thing is doing, it's looking out at the cosmos, and particles coming down, and it's detecting them. It's got a particle detector, a sort of miniature version of CMS and Atlas in there, and it's trying to reconstruct the charge and mass of the particles by their trajectory as they go through there. And one of the things it's looking for is antiparticles, but not just antiparticles, antinuclei. So it's looking for antinuclei of the sort, because the heavier nuclei in the universe were created in stars and are there because of supernovae, and are out in the universe because of supernovae explosions. So they're looking for heavy antinuclei, like an anti-alpha atom or an anti-carbon nucleus, to see if there have been any anti-stars or any galaxies out there. So that's one way to try and by the way, every time we look for antimatter in the cosmos, we find none. And this experiment is just up there recently and is starting to take its first data. Another way to approach this is to study antimatter on Earth, and this is just a second, and this is just a second, please. And this is what I do. So now I'm going to describe an experiment. We've got positrons and antiprotons. We've had them for ages. And in the last 40 years, we've learned how to control them and make them into beams and to manipulate them. So now I'm going to turn the energy wick down from the LHC all the way down below room temperature, down towards absolute zero. And I'm going to tell you about some particle physics experiments that are being done below 1 degree Kelvin at CERN. So if you can start this off, I'm just going to talk you through, I'm going to finish with this animation, and I'll talk you through our experiment. So our experiment is to make atoms of antihydrogen, okay, to join together positrons and antiprotons. They're antiparticles, so if they hit matter, is it running? If they hit matter, they will annihilate promptly. So the antiparticles, we have to keep them away from all matter. And so we do that by constructing an apparatus with a vacuum chamber. That's that thing there, just schematically. What you're seeing here is a detector, a little bit like Tom's detectors, except a very simple one. These are layers of silicon which detect actually pion particles when they come out. So inside this thing, we had a set of electrodes which we apply voltages to. I've got one of them here, so this is very small physics to do particle physics with. We have to hold on to the antimatter. It's frozen again. Okay, don't worry. So we have to hold on to the anti-atom. So we erect around this trap a trap for the neutral. You might think, well, how do you trap a neutral? But a neutral has a property called spin, and if you erect a magnetic field minimum, you can hold an atom in that minimum. Okay, all right. So we're energizing these coils now. So these are coils with current running through them. They're superconducting coils with thousands of amps running through them. And it stops again for a while, maybe not. And here are the electrodes on the inside. So these are the electrodes that we apply a voltage to. And we have our positrons and antiprotons inside there. And here they come. So we apply a voltage. One of them is positively charged, the positron, and one is negatively charged. So the positrons like to sit downwards and the antiprotons. And they bounce backwards and forwards in there, a little bit like a clock. And we give them a little bit of a kick to get them outside of that well, and when they pop out, they pop into the positron cloud. So they're just held in little rings like this, and when they go inside, there are enough positrons inside there that this antiproton will meet two of them at once. One of them will bounce off, it will become a spectator, and the other one will be captured by the antiproton. And that is an antihydrogen atom. Why do we want to study this? Well, we want to try and measure the properties of this thing. And the reason we want to do this is because the hydrogen atom... So here it is, we've built this magnetic trough, and this thing has got a spin which is preventing it from hitting the wall, and it's bouncing around with a kinetic energy equivalent or a temperature less than half a Kelvin. What we then do is we remove the magnetic field, and the antihydrogen goes on the outside, and the antiproton annihilates. So we've been able to do that experiment. What we've been able to do now is, in the last part of this animation, if we get to it, is we've been able to perform an experiment on this antihydrogen using microwaves. So these are microwaves which we beam down the axis of this pipe. Nature was, and so the antihydrogen, it's the magnetic moment that keeps it inside. This is the spin pointing along. The microwaves come along, they flip the spin round, and it becomes untrapped and disappears. So the microwaves flip this trapped antihydrogen atom into an untrapped one. And bang, it goes out of the trap. So if you want to just put the last slide on for me, Tom. So these events that we've seen, we now know that the antihydrogen transition for that, these are the extra events caused by the annihilations on resonance. We've measured the position of that. This is a quantum transition. This is what we're about in atomic and particle physics, often quantum transitions. We've measured the precision of that to 1 part in 1,000, which sounds a lot. But in hydrogen, the equivalent is known to 1 part in 1,000 billion. Okay? And that's not even precise. There are many more precise. So what we're doing here is we're doing particle physics at zero energy, trying to look for a chink in nature's armor to try and answer one of these big questions that are left. Thanks, Tom.
Great. So, I mean, the problem of antimatter is one of the huge things. It really is about understanding where it all went and why we're all made of matter in the first place, and why there aren't these universes of matter and then antimatter that should have been created when everything else was. But there are other big questions too. Is supersymmetry dead? So the LHC was promised many sort of things in new physics, not just the Higgs, but this idea of supersymmetric particles or shadow particles that sort of existed. We didn't find those. That was what my PhD was looking for. I mean, that's still a result, right? I mean, they still gave me a PhD, but they're not that dead yet. I mean, they're not there yet. So we've got to wait until 2015 when we switch it back on at double the energy to have another look. So until then, I've got a bit of a break to do this sort of thing. So what is very closely related to that is what is dark matter? What is this stuff that apparently makes up 20-odd% of the universe, the whole universe, that we just have no idea about? We think it might be related to supersymmetry, and that supersymmetric particles might be this sort of shadow matter that makes up a large chunk of our universe. But again, we don't know. But there are other experiments looking on the ground that are looking for particles of dark matter that are just sort of passing through and creating signals like that. Again, one of the big questions we don't understand. Where does gravity fit in? So the standard model, I mentioned there are three forces there, the strong force, the weak force, and the electromagnetic force. The fourth fundamental force of nature is, of course, gravity, and we've just got no idea at the moment how to fit gravity into this big picture of how matter and forces work. So that's an area of intense research and where we need to understand a lot more about the universe, and hopefully we'll do something like that. And again, related to that, will we ever have a grand unified theory of everything? Will we be able to explain or describe all of physics in, hopefully an equation which is a lot simpler and more elegant than the one we saw earlier? But, it would be nice to just have a single line thing like a Dirac's antimatter one. But will we ever have that? We just don't know quite yet. And do neutrinos have all the answers? Now, again, we've only had 40 minutes to this, but there's a whole world of neutrino physics where studying these strange ghost-like particles that we only have just found out actually have mass, and that's not in the standard model. That's already physics which really is beyond this picture that we already have, that they oscillate between different types, and that means they have mass too. Do neutrinos hold the key to answering these sort of questions if we can't go any further with accelerators or the LHC? And maybe we'll touch on that in the question session. I don't know. But yes, there's still a lot more to do. And that's part of the joy of particle physics, and this kind of journey to find out what we're all made of, what everything in the universe is fundamentally made of, whether it's matter or indeed antimatter. That's what particle physics is all about. And so I'll just end with it. If you wanted to find out more about particle physics, i.e. the bits that we couldn't quite get in here, funnily enough, I do have a book coming out in September, which is it's a slightly twist on the title. It's Introducing Particle Physics, not Particle Physics, an introduction, but it's a graphic guide that will take you through this 100-year journey to find out what we're really, and that'll be available in all good bookstores on the 5th of September. But thank you very much for listening, for coming along today, and thank you as well to Professor Mike Charlton for providing the expert insights into the antimatter universe. And thank you very much. That's everything.
All right, they're not going anywhere. So we've now got just under a quarter of an hour to take some questions. We have 4 roaming microphones. Please do not ask a question unless you are holding the talking mic. And then please try and talk into it as well as you can. It should be closer to your chin than you expect. And there are more questions than we're going to be able to get through. So we'll do our absolute best. If you have got a question, can you just ask a single question? And before you say it, can you double check the end of your question for the presence of a question mark? I'm sure there are some great statements people would love to share, but if it's not technically a question, I will just make fun of you. Okay, so where are the roaming mics at? Okay, there's one over here, there's one over there. We'll try and load up. So if you guys could, there's a question on the end there. If you mic people, find someone with a question near where you are, and then I'll go around in semi-quick succession. Okay, so there's one right down the front. So I'm going to start with the guy right on the end who's got fantastic microphone technique.
Thank you very much. In terms of finding a compatibility between general relativity theory, which requires gravity amongst its four fundamental forces, and quantum, such as quantum exists at the moment, would one way forward be to, stay with superstring theory and hope that that provides the solution, or, if you prefer, you might not want to hear this, but if you alternatively decide to jettison the idea that there are quanta packets, that is, of energy, and that quantum theory has to fundamentally change its assumption. Thank you.
So the question is, might you not just be wrong? Okay.
Well, trust me, we would love to. Do I use the? We would love to jettison quantum theory because it is absolutely and completely crazy. It makes absolutely no sense. It says that photons explore every possible thing. It says that cats should be alive and dead. It's not good.
Seems to be true, though.
But yes, well, this is the problem. Every experiment that we do to try and either disprove it or show that it's wrong keeps coming back saying, no, this is how the universe works. This is how every possibility is explored. The universe does just work by quantum theory. But yes, this idea that we're kind of trapped in a sort of this paradigm of so the standard model is a branch of quantum field theory, which and even in itself is a lot of approximations and stuff in there. And is there something more beautiful and elegant? Well, it could be. So we'll just have to keep throwing more money at it, I think, is definitely the best thing to do. And keep looking. That would be my...
I think there will be some experiments in the next few years in which the particle energies are low enough that you'll be able to explore the individual quantum gravity states. So that might be a way forward experimentally too. But as far as I understand it, the only theoretical route forward is through some kind of string theory at the moment. There doesn't seem to be any other hope of incorporating gravity into a quantum theory.
Okay. So the answer is we hope we're wrong. Okay, so we're going to go into the front row and then we'll go over there in a second. So,
you mentioned one of the great unanswered questions is about the origin of gravity. Are there any favourite speculations about it?
Well, in terms of fitting it into a quantum field, people would hope that something like the graviton would explain how gravity works. As in, it's similar to the gluons and the photons and the W's and Z's, so it just fits in. But for gravity to work like that, you have to have a spin 2 particle, which we've never sort of observed. So that's kind of what people are pinning their hopes on, I guess. But, yeah.
Gravity is a really difficult topic because we have a wonderful theory of it, which is completely classical. And we've not even observed gravitational waves yet, let alone a particle which might accompany a wave. So we're a long way behind with gravity, curiously, which was the force that was discovered first.
Okay, we'll go over here. Yep, and then we'll come back down the front next.
Hi, it might be because I'm not as clued up about it, but if the Large Hadron Collider was to be in space, would the results be any different due to the lack of gravity?
So the question is, the collider wasn't expensive enough to start with. What if we put it in orbit?
I'm sure some people would like to put it in orbit. I believe that the results would be identical.
Yes, I don't think the presence of a gravitational field would... in some ways it'd be more expensive, but of course it would be... you'd have a far smaller cooling bill. So these superconducting magnets that you
It's arguments
have.
like this is why we ended up with it in the first place.
So rather than having to cool down... So you've got this 27-kilometre underground, essentially sort of bit of vacuum, which is... it's a few degrees Kelvin. It's colder than that. It's 1.93 degrees Kelvin. It's colder than that space. It's essentially a ring of outer space under the ground. So in that sense... building the ring up out in space, you could probably do it build it bigger as well. That was the limiting factor on the size of the LHC, was the mountains and the sort of city around it. So in some ways, yeah, doing it in space would be a great idea, and I'd love to be one of the astronaut physicists. Because you'd need them, right? You'd need them to, make sure it was working properly.
You have a lot to answer for.
Yeah.
Okay, I think we've given that more treatment than expected. Okay, down the front here.
Yeah, going back to the progress of the Big Bang, just to explain something about the diagram and why you created anti-hydrogen atoms. Did the antimatter particles disappear before they had a chance to create the hydrogen atom, anti-hydrogen later on? And are you creating anti-hydrogen simply so that you can observe the disintegrations?
Yes, you're absolutely right. I'm sorry if I didn't make that clear, but the antiparticles disappeared for reasons which we don't understand. And the universe that remained is 1 part in a billion, roughly, of what it was before they disappeared. So by the time the universe had cooled right down enough to be something like the temperature here on Earth, there were only particles left. So we're creating the anti-hydrogen atom to perform experiments on it, to test it at a very high level to see if it's identical to hydrogen. But essentially, you're exactly right, yes.
Excellent. Now, we've still got a few more mics roaming around. We're going to go to Miss over there. If we pass it down. Oh, we're over here. Okay, yep, that works just as well. Okay, so we'll go Sir in the centre. And then was there a lady with a hand up? She's now scratching her head. She's now looking a bit nervous that I'm pointing at her. If we can get it, we'll go to you next if we can get that mic passed down. Okay, in the middle.
Okay, thank you. Do the presence of the heavier quarks, the top, bottom, strange and charm, actually do anything, or does that point to there being a more fundamental theory sitting over everything?
In the sense of do they do anything? No, not really. I mean, in the sense of our everyday experience, everything's made of up and downs, and they don't really do. What they do affect is the calculations of things like the Higgs mass, for example. So there are sort of loop corrections that you do when you calculate other properties of the universe, and that's one way that we would perhaps even discover things like supersymmetry through the back door. So if you had sort of these virtual particles that were very massive, like the top and the bottom quarks were, they would contribute to these values that we can actually measure without having to smash stuff together in the Large Hadron Collider. So their influence is kind of subtly inferred through this crazy quantum mechanics stuff, because everything that can possibly happen does happen, but to varying degrees of probability. So their effects are there, but there's no overbearing effect on our everyday lives. I think that's probably fair to say.
The answer to that question is exactly why we do anti-hydrogen research. It's buried deep in the spectrum. There may be a difference due to the influence of these particles, even although they don't currently don't exist in reality, but they can be felt if you make precise enough measurements. Their effects can be felt. It's quite remarkable, really.
So they don't do anything other than annoy physicists. Okay, so Miss over here.
Is dark matter the same as antimatter, or is that something different?
It's something different.
Okay.
No, it's good because you can have anti-dark matter as well. So you've got matter, dark matter, antimatter, and anti-dark matter. And actually, there's a serious point here in that one way of looking for dark matter is for looking for dark matter annihilating with anti-dark matter and creating an excess of positrons that you would actually observe with the AMS experiment as well. So that's another thing the space-based LHC, if you will, is looking for. It's looking for an excess of antimatter which comes from these dark matter, anti-dark matter. So it's a completely brilliant question because it lets me talk about another AMS result, which is, I mean, they had their first sort of results recently, and they're sort of interesting. They suggest that there may be sort of hints of dark matter out there, but more research and more money is needed. So do give generously to the Dark Matter Search Fund.
If anyone asks a question about dark energy, you will be escorted from the tent. Okay, so we have a question over here on the end.
I'm still confused as to why we're confused about gravity. So my understanding was that Einstein said it's not really a force in its own right, and it's just a function of the way the universe is actually 4D, and that's why you get gravitational lensing and light bends and all that kind of stuff. If why is that wrong, and why do we therefore need waves and particles to explain how gravity works?
I'm not sure that it's wrong. It's probably a limit of another theory, is all I understand about it. That it's a little bit, the situation seems to me to be a little bit like classical mechanics was before quantum mechanics came along. And classical mechanics is still a very fine theory in its own area, but sooner or later you need to take quantum effects into account. It's just that the conditions you need, as far as I understand it, to take quantum effects into account in gravity are very extreme, and it's very hard to observe them. But there's nothing intrinsically wrong with the description for most of the universe of general relativity, as far as I understand it.
I mean, it's more a matter of elegance in the sense that for a grand unified theory of physics that would describe everything, ideally you'd describe it all in the same way. So with the standard model, it's this idea of matter particles and force particles. So what you want to do is crowbar gravity into that paradigm, that model of having things like gravitons, which explain how the gravity... But in terms of technically every theory is wrong, right? I mean, everything is wrong until you find an approximation, which is just approximations of how the universe works. And we've got these two beautiful approximations that are both described beautifully by experiment, but it's trying to just bring them together and make them consistent. That's the problem, which is why we should give theoretical physicists more money. There's a theme.
But if we can't make them consistent, that will also be incredible. If for some reason, deep reason that we don't understand.
Could we prove that there's no way of...
No, we can't.
No,
we just keep on looking, and then we
might
find it a phenomenon that we don't expect.
But if we say that, they might not give us any more money.
No, we're keeping on looking. You're fixated on money. Yeah.
Physics, it's more expensive than maths, and technically always incorrect. Okay, so we have time for one very last question. I'm going to go, for simplicity's sake, sorry everyone else, with Miss right down the front here.
Would Dirac be spinning in his grave if he realised how much this was costing the Exchequer?
All right, so would Dirac have a half spin if he knew just how expensive all this is?
I probably wouldn't notice too much. If you believe the stories about Dirac, I mean, I can't imagine how he would react to what's happened. I think he'd be thrilled that his particle has found practical applications in medicine, for instance. So he might be spinning one way one day and one way the other day. But the spin is absolutely crucial to Dirac's equation as well, of course. It sounds like you knew that from the question you asked.
I like to see you put a question mark on it, and that's what counts. Okay, on that note, we're going to have to wrap up. Thank you all very much for your questions. Have a final huge round of applause for Mike and Tom. Thank you.